Welcome all to another session of TIFR Math problem solving. So the problem today is closely linked to one of the problems that we see quite often whenever we are introduced to connectedness, path connectedness, stuff like that. So here the question is, if A is a collection of countable, A is the union of countably many lines in R3, then R3 minus A is connected. Is it true or false? So we will tackle this one by one, like dimension by dimension. So first of all, if I have R, and from R, if I remove any point, then this becomes disconnected, right? All right. So from R, if you remove any points, any single point, let's say x naught, then it becomes disconnected. But this is to the contrast in R2. In R2, if you move any point, if you remove any point, so it remains path connected. It's not even only connected, but it is path connected. So R2 minus x naught y naught is path connected. And this is also true when we are actually doing this R2 minus countably many points. Even if we do this, even if we take, fact is because like R2 has uncountably many points, and the path connectedness means that if you pick any 2 points, then there has to be a continuous path that joins these 2 points. Let's say P1, P2. So if I only remove countably many points, then since R2 has uncountably many points, I can always find those extra points to dot my path through. So that's the geometric way to understand this. Now in R3, so now surprisingly what happens that in R2, if I remove a line, then it loses the connectedness property. So suppose now actually removing this blue line from R2. So this is also never ending. Okay, so it's an unbounded line. So that's the difference between a line segment and a line. So if I actually take this like R2 minus L, so as you can see that it doesn't remain path connected, let alone connected. So see, because of the fact that if you pick any 2 points, here and here, there cannot exist any path in R2 minus this R2 minus this line segment space, so that your P1 and P2 are getting connected, right? So there is no path connectedness here. And also, since you have actually removed this single line, then what happens is this becomes an open space, union of 2 open sets in R2. So thus R2 minus L can be written as 2 disjoint union of open subsets of R2 minus L. Hence, it becomes disconnected. So as you can see, there is a pattern here. So whenever I'm actually removing a point from R, it is becoming disconnected. But removing a point from R2 is not making it disconnected. It is even path connected. But removing a single line or countably many lines from R2 makes it disconnected. So this is the concept, or this is the section that gets generalized in this problem. So in this problem, what you have, so just like we went from here to here, now we are going for a ride from R2 minus L to first, let's see what happens at R3 minus a line. So let's see what happens in R3 minus a line. So in R3, if you remove a line, then it remains path connected. Can you see by this same logic that I have used here for removing a point in R2, why is it becoming path connected? By that same argument, you can actually write down that R3 minus L is always path connected. So geometrically, what actually happens? So geometrically, if you take R3, so if you take R3 and if you remove a line, let's say you remove any line, let's say for this, then here there is no point. I mean, here there is no like we are not facing any kind of problems to connect any two points that are present in R3 minus L, because as you can see that if I put any 2 points, then I don't need to go over this line. I mean, I don't need to go through this line. I can actually go around this line to meet here. Okay, so thus R3 minus L, R3 minus a single line is always path connected. Now that's the same thing that happens when we take R3 minus countable union of lines. So how does that actually happen? Like it is practically like this, that see R2 minus countably many points is path connected. Similarly, R3 minus countably many lines will also be path connected. So see in R3, let me draw this picture again. So in R3, what happens is, if you take any 2 points, you can construct a sphere on whose surface these points are actually lying. All right. So let's say like this, if you take this as P1 and P2, so what you can do is you can actually form a great circle like this that contains your P1 and P2, and from there you can generate your sphere. Okay, so moral of the story is, given any 2 points, you can actually always construct a sphere that contains P1 and P2 in its surface. All right. So now if you are actually removing countably many lines from R3, then there is a possibility that you are also removing countably many lines that is passing through this sphere. Because see, if none of those lines that you are removing from R3 is passing through the sphere, then there is always a path that connects P1 and P2 quite trivially, right? The only problem is, whenever among those countably many lines, a small amount of countably many lines pass through the sphere, or let's say all of them pass through that sphere. So what happens if all of these passes through sphere, or let's say I mean countably many lines pass through sphere? So this sphere is now embedded in R3. Okay, so and now let's say that it is passing through, there are countably many lines that are passing through like this sphere. So what happens is that countably many lines pass, I mean if you take R3 minus L, sorry, so let's say capital L, or have, let me just make sure what, yeah, A, alright, so A be the countable union. So R3 minus A. So if you take R3 minus A, so then in an embedding setup of the sphere, you are actually removing these points. All right. So R3 minus A is nothing but, in this sphere is nothing but removing 2 into that many countably many number of points. Okay, because if it is passing through the sphere, if it is passing through the sphere, then it is hitting the sphere in 2 points. All right. So that means what? That means R3 minus A in this situation, in this embedding situation, you have S2. So let's not make a unit sphere. So let's call this any sphere S. So S that contains P1 and P2. So this minus A is nothing but so S containing P1 comma P2 minus A is nothing but removing countably many points from S P1 P2. So now removing countably many points from S P1 P2 is exactly the same scenario when you are actually removing countably many points from R2. Okay, so hence this is always path connected. Now if you have an embedded space in R3 minus A that contains that 2 points, in those 2 points you started to work with, which is becoming path connected, it implies that R3 minus A is path connected. Okay, so what are we actually doing? So if I go step by step once more, what we're actually doing, first we are taking any 2 points, then we are constructing a sphere in R3 such that those 2 points lie on the surface of the sphere, which can always be done. So now we are proving that there always exists a path on the sphere even after removing countably many lines that joins P1 and P2. Hence there always exists a path real on R3 minus A that joins these 2 points. Hence it becomes path connected. Okay, so now path connected implies connectedness. Thus we have this as, yes, this is true. Okay, so countable union of lines, if you remove it from R3, they remain path connected, hence connect. So thank you for joining. We will meet again with another problem from TIFR next time.